I'm back again. So this is going to be part number 2 of collective communications. We're going to continue from where we left off. We were talking about this bidirectional data transfer nature of this example of all gather, for example. And then we said these operations, which they have this communication pattern of all to all, they have this bidirectional data transfer pattern. And but the operations one to all and the category of all to one, they have this unidirectional data transfer sort of layout. And in this rationale also talks about operations in all to one and one to all categories are unidirectional by nature, and there is a clear way of specifying direction. Operations in all to all category will often occur as part of an exchange where it makes sense to communicate in both directions. So barrier synchronization, this is going to be the first, let's say the first communication operation or collective communication operation that we're gonna learn today. We have an example MPI barrier.c, but first let's take a look at the semantics. If communicator is an intra-communicator, MPI barrier blocks the caller until all group members have called it. The call returns at any MPI process only and only after all group members of that communicator have entered the call. So let's go back and take a look at this example, MPI barrier.c. This is super simple. We're just going to print a hello statement with the specifying our rank. And then finally, we have this synchronizing barrier call. We pass in MPI world come or come world. This is sort of the default communicator that MPI provides to us, which contains all the processes that you basically invoke when you call them. When you say, for example, MPI run minus NP5, 10, 20, or whatever, those number of processes, all of them are going to be used with this sort of communicator, MPI come world. And then after that, we're going to have a by statement. So notice that there is no guarantee of sort of the order of the calls here for the first statement, but it is guaranteed because we have a synchronizing barrier call here. It is guaranteed that this statement is going to get executed before the by statement, because everybody is going to get stuck here up until to the point that every process basically prints this hello statement, and then everybody can come and print the by statement. So let's go MPI-CC MPI barrier. .c and MPI run. So with 5 processes, it's going to be the same. So hello comes first, and then by comes next. If communicator is an inter-communicator, then the semantics are a little bit different. MPI barrier involves 2 groups. The call returns at MPI process in one group, group number A, of the intercommunicator only after all members of the other group, which is group B, have entered the call, and vice versa. So if you're in group A, a process in group A, you can only return from MPI barrier with the condition that all the processes in group B have entered the call in MPI barrier. And if you're a member of group B, a process in group B, then you can only return from MPI barrier only in the condition that all processes in group A have entered the call in MPI barrier. So this is sort of the MPI, the intercommunicator version of MPI barrier. So you kind of get the idea that all sort of the examples that we have here is going to have this symmetry, that we have the bare bone sort of operation, and then we're going to have an operation which has this underscore inter, which shows basically the intercommunicator context. So this example is much lengthier than the previous one. I'm not going to comment on anything here. So basically know that all the way up to this point, whatever we do is basically we try to create 2 communicators, communicator A, communicator B, and then with the help of this intercommunicator, we want to communicate or try to execute this operation in the context of intercommunicator. So notice that we are not passing MPI come world here, but we are passing the intercommunicator between 2 communicators, communicator A and communicator B. The same drill goes here for hello and bye. So let's MPI-CC, MPI barrier, inter, MPI run it. So we get the same behavior, but this time, as I said, it's in the context of intercommunicators. The next thing we're going to learn is broadcasting. It needs buffer, count, data type. So you have seen this pattern like a trillion times already in point-to-point communication. For example, in MPI send, we always have send, buffer, count, and then data type. The same goes for broadcasting, but then extra to that, you need a root here. Why do we need the root? If you take a look at this picture again, so there's always one process that has the information, that is the root process, and and that is the process basically responsible to send that information to every other process in that communicator. So that is why we have the root. It's simply an integer. We're going to see it here. Whoops. Here. It's simply an integer. It shows the rank of the root process. And then we have here the communicator, which gives you the context of communication. Again, semantics. If communicator is an intra-communicator, MPI bcast broadcasts a message from the MPI process with rank root to all MPI processes of that group, itself included. So it's going to broadcast it to itself included. It is called by all members of the group using the same arguments for communicator and root. On return, the content of the root's buffer is going to get copied onto all other MPI processes buffers. So here we have MPI, Vim MPI bcast. Whoops. So again, very simple example. A buffer is an integer. It's not initialized for all the other processes. It is only initialized at root process or process with rank 0. So accessing this buffer on other processes is dangerous because this thing is not initialized. But MPI bcast, so process number 0, or the root process, is going to broadcast this buffer number 7 into all the other buffers of the other processes. So we have the buffer, we have the count, we have the data type. This is the root process. And then we have the communicator, that is the, so this is the case of intra-communicator. And then every process is going to print its own buffer, including the root process. So MPI CC, MPI bcast, and MPI run. You see that every process, including the root process, has the same value of 7 for the buffer. Now semantics for sort of, so note that the in-place option is not meaningful here. And if communicator is an inter-communicator, so that is the semantics for inter-communicator, then the call involves all MPI processes in the inter-communicator, but with one group, which is group A, let's say, defining the root, and all MPI processes in the other group, group B, pass the same value in argument root, which is the rank of the root process in group A. The root passes the value MPI root to root, and all other MPI processes in group A need to pass the value of MPI proc_null as the root argument. So we're going to see that in a second. So it's getting a little bit more complicated compared to the intra-communicator, right? So data is broadcast from the root process in group A to all MPI processes in group B. So that is what it means if you are broadcasting in the context of inter-communicator. It means that one process in group A is going to be the root, and it's going to send the message to all processes in group B. That is the drill, basically. Then we have an example here, MPI bcast, MPI bcast inter. The same symmetry goes here. Again, we're not going to talk about these things because we haven't talked about communicators and stuff like that. So just don't mind these things. Up until this point, again, just imagine that we have two communicators, A and B. We have a buffer. And this color is, again, something we use for splitting those processes to different communicators. So let's say this is local rank 0. This is going to be the root process, which is inside group A. It's going to initialize that buffer. So everybody has this buffer, its own copy of the buffer. It's not initialized. So only root process in group A is going to initialize this value to 7. And then it's going to say that, hey, I'm root in group A, I have the world rank of that, and then I'm broadcasting the buffer. And then this is the important part that we were talking about here. We said all MPI processes, where is it? Boom, boom, boom. Yeah, the root needs to pass MPI root as the root argument because bcast needs a root, right? Bcast needs a root. So everybody, all the processes are going to see this call here, this MPI bcast, but the root is going to be different for each one. Why? Depending on the color here. So MPI root is going to pass MPI root as the root argument. And if you are in group A and your rank is not the root rank, is not 0, then you need to pass MPI proc null as the root. So this is what it says here. They need to pass in MPI proc null if they are processes in group A. So that is why we pass in MPI proc null here. And otherwise, if you are in group B, you need to pass basically the rank of the root process in group A, which is 0. So that is why we have this basically few lines of code here to set up the root properly. And then finally, this is color 1, which means that now we are talking with the processes in group B. They're going to print sort of the buffer that they have received from the root process in group A. So MPI CC, MPI bcast, inter, and then we're going to have MPI run. So you see that root in group A, which has the world rank of 0, is broadcasting buffer of 7, and proc 2, 3, and 4, they're in group B. So processes 0 and 1, they construct a group number A or group A, and processes 2, 3, and 4, they're going to construct group number B with the same buffer. This is the message that they have received from root process in group A. Then we're not going to take a look at this example because we have our own examples. The next one is going to be gather on the line. So we have an example of MPI gather.c. So this takes a billions of arguments. It takes send buffer, count, type, receive buffer, count, type. Again, this sort of pattern, you have seen it a lot of times. And then it gets a root again because, again, if you take a look at this gather, that picture. So this is the gather. So there needs to be one process, which is going to be the root process, that gets all these information, or it collects all the information from other processes. So in this case, A0 to A5 are sort of being copied inside process number 0, right? So that is the root process, basically. Let me find this gather again. So that is why we have a root here, and then communicator again, which is sort of the context of communication. Notice that these receive buffers, receive count, and receive type is only important and only significant at root process. Why? Because only the root process is going to take the results from other processes. No other process is going to receive anything from the other processes. So this is why these receive a buffer, count, and type is only significant at the root process. Okay, so this is a little bit of the semantics here. It says if com is an intra-communicator, each MPI process, the root included, sends the contents of its send buffer to the root. The root receives the message and stores them in rank order. This is what we talked about earlier in part number 1. The outcome is as if each of the n MPI processes in the group, including the root, has executed a call to MPI send with a send buffer, with a send count, with a send type, and to the root. And the root had executed n calls to MPI receive, but each time the receive buffer is going to get sort of displaced by how much, or what is the extent, what is the amount. The amount depends on I, which is sort of the rank of that process, on the count, how many items we are receiving, and on the extent. So If you are using like MPI int, what is the extent of that int? So that is basically how much that that receive buffer is going to get displaced. Where extent is sort of the extent obtained from the call to MPI type get extent. So this is when, for example, you're using a general data type. Okay, that's for the semantics. So it also gives an alternative description. We're not going to take a look at that. So this is basically something which you can imagine in your head what happens. So now we go to which point is important. Let me take a look at it. Okay, it says note that the receive count argument at the root indicates the number of items it receives from each MPI process, not the total number of items that it receives. This is also important. The in-place option for intra-communicators is specified by passing MPI in place as the value of send buffer at the root. And this means in such a case, send count and send type are ignored. So these two things are basically not important, not significant at all. And the contribution of the root to the gathered vector is assumed to be already in the correct place in the receive buffer. So that is what is implied if you pass in MPI in place as the send buffer when you're working with intra-communicators. So let's go with MPI gather.c. So again, these things not relevant, or we already have talked about them. But for example, we put a sort of a restriction here that you need to use 8 processes for this MPI gather example. But you can also ignore this thing. So here we have a send buffer. Everybody is gonna put its own rank into send buffer. So they are uniquely sort of initializing this send buffer. Then we have a pointer receive buffer. It's gonna be a null pointer. And then, so here this example takes a look at two things to be sent. One is an integer and the other thing is a C string sort of character. So the reason that I put here is that, like, you know that C strings are source of a lot of issues in sort of C programming language. So if you can implement something which works with C strings, then probably you can implement whatever you want in C. So that's why we have put it into 2 portions, one being integer and the other one being working with C strings. And another significant thing that I wanted to stress here is that for integers, I'm going to send the buffer, but for the strings, I'm going to use the MPI in place. So that is another reason why I use sort of 2 different buffers for that, because I wanted to also show you how to use MPI in place. So send buffer is uniquely sort of initialized, and strings, or the send a string, is also uniquely initialized with dynamically with the rank included. So it's going to be hello with %d, which this %d is going to get populated by the rank of each process. And also notice that 10 is sort of the maximum amount of buffers needed for this send a string. It doesn't mean that necessarily we're going to use all those 10s. For example, in this case, we have 1, 2, 3, 4, 5, 6, including the null character is going to be 7. But we have the space for 10 sort of characters. So rank number 0 is going to have the proper sort of buffers. Why only rank number 0? Because this is a gather operation. So I could put this receive buffer, the definition outside. But the thing is, I'm going to sort of allocate the space on other processes, which is not needed basically, because we are working with a gather operation that everybody contributes in the result, but only one process, which is the root process, is going to get the results. So a sane idea is that only one process should allocate sort of data as big as those, let's say, messages sent from every process. So you see that we have a size here as well. I kind of messed up with the explanation, but you see that you see that the receive buffer needs to be as big as the size of processes you have multiplied by the size of the integer you have. Because process number 0 is going to get all the results from all the other processes. So it needs to have a receive buffer which holds a sort of size number or n number of sort of integers, n being the number of processes used. So receive a string the same way. It's going to be size multiplied by 10 because our string buffer has 10 and size of character. And then we call MPI gather, send buffer count integer, receive buffer count integer. Again, receive buffer is going to be 1 because we receive 1 buffer from every process. And this count is not the total amount received. The total amount received is equal to the n number of sort of integers, and n being the number of sort of processes. So in the second form, so this is the MPI gather call. We do it. And then for the second call, for the rank 0, since I want to use MPI in place, I need to prepare the receive buffer for the 0th, let's say, element, or the 0th string is going to get populated with the send string that we had outside already defined right here, because we are going to use the receive buffer. So we are assuming that the receive buffer is already ready, the result are already ready and placed there. So we are using MPI in place this time instead of the send buffer. And then everything is going to be the same. So but the difference is that the count is 10 here instead of 1 because we have 10 sort of characters. And all the other processes other than rank 0, they are going to have this version of MPI gather, which they send a string. That's a different buffer. That's the buffer here we defined. And then 10 characters, MPI character, that's the type, receiving string, and then 10 characters, MPI char. And that's how it basically works. And then on process number 0, which is the root process, you're going to print the result. You're going to print sort of that vector that you can assemble, or that array that you can assemble from getting all the integer results from all the other processes. And you're going to have another array which you get all the results of those CString style texts or strings from all the other processes, and then concatenate them into this buffer. And then finally, since receive buffer and receive a string were dynamically allocated with malloc, then once you're inside rank 0, then you need to free those resources because you're done. You printed the results. So let's take a look at MPI gather and MPI run. I think we sort of put this restriction that we need to have 8 processes. So there we go. Everybody sends the information to process 0. Whoops. So here is the mark of 23 minutes. We're going to finish soon, and then we're going to basically start the new episode, which is going to be the part number 3. So now you see that the root or process 0 has sort of a buffer as big as the number of processes, and it is populated with sort of the unique information which was taken from different processes. And the receive string has also hello with a number associated to it. That number sort of signifies the rank of that process. And you see that every process number 1, 2, 3, 4, 5, and up until 7, they successfully transferred that send buffer to the receive string. Okay, I'm going to stop here, and then we're going to start the next sort of part.